All right, welcome back. We're going to pick up with example 3 before we get into section 3. So we've got one more question here that's asking us about internal energy. So let's go ahead and look at number 3. A system undergoes a change in internal energy of negative 32 joules. If the system absorbed 45 joules of heat, what was the work done during this process? Did the system do the work or the surroundings? And then finally, what does that tell you about the change in volume of the system? Wow, we got a lot going on. Okay, let's just take it bit by bit, piece by piece. So this time, so delta U equals Q plus W. But this time, we actually are not solving for a change in internal energy because we know that. What are we solving for? We're solving for the work, right? So I'm going to rewrite this equation. Picked the worst color, of course, but I'm going to rewrite it so that we have work is equal to change in internal energy minus Q. Okay, so I just rewrote the equation so that way we're solving for W. All right, let me go back to a normal color so it shows up a little better. So, all right, work is equal to, what was the change in internal energy? What was my delta U? We are told that the change in internal energy was negative 32 joules. All right, so negative 32 joules. And then minus, now be careful, the minus has nothing to do with the sign of heat. We still need to take that into consideration. It's just minus because of the way we rewrote the equation. So it says the system absorbed 45 joules of heat. So what is the sign when the system absorbs heat? It's positive. So it's minus a positive 45 joules. All right, so what would that come out to be? So we're going to do negative 32 minus a positive 45. We end up getting that the work is negative 77 joules of energy. All right, so the work is negative 77. So what then can we answer? How can we answer the rest of these questions here? Right? So it says, okay, did the system do the work or the surroundings? So notice the work is negative. So what does that mean? When the work is negative, what's doing the work? The system or the surroundings? And the answer is the system. Okay, the system is doing the work if it's negative. Okay, what then does that tell you about the change in volume? So to answer that question, let me go back to this drawing right here. So remember, when the system is doing work, and I have my little guy here, okay, you're inside, you're doing the work, you're pushing, right? You're going to push that piston up, which what does that tell you about the volume? Volume is increasing, right? And so volume is increasing. Okay, if the system's doing the work, the volume is increasing. All right, so that's how you'd answer example number 3. So without further ado, let us now get into section 3. And section 3 is beginning to define this word called enthalpy. The rest of this topic is brought to you by the word enthalpy. So we're going to talk about what it is, and then we're going to talk about how you figure it out. Okay, enthalpy has the symbol H, right? So enthalpy, or H, stands for heat content. Okay, heat content absorbed or released in a system under constant pressure. Okay, now, you're like, what? What's going on? So, lots going on. We're going to try to make this as easy as possible. You may remember seeing delta H in previous topics. I know we saw it in topic, I want to say topic 9. We also saw it in topic 8, because remember we had heat of vaporization, heat of fusion, and all that stuff. So delta H, it stands for change in enthalpy, because going right along with the pattern of this unit, we can't calculate enthalpy, but we can calculate the change, and that's what we care about anyway. So the change in enthalpy, or delta H, is just the change in heat content that's absorbed or released by a system under constant pressure. Now here's the thing. Most of the reactions that we do, in fact, all the reactions that we do in Chem 151 are always done under constant pressure, meaning that pressure is not going to build up, let's say in a steel tank, for example, pressure is allowed to kind of equalize itself out. So all that to say, as long as the pressure is constant, which it always will be in Chem 151, enthalpy is the same as heat. Same thing, okay? It's the exact same thing. So that's nice, right? So enthalpy is just a fancy schmancy word for heat. That's all it is, heat. As long as pressure is constant. Now, what happens when pressure is not constant? Well, then enthalpy is different from heat, and then you've got some further calculations that you have to do, which you have to do in later chemistry. You're not going to worry about it in 151. So all that to say, enthalpy is heat. And when we're looking at a chemical reaction, we're looking at the change in enthalpy. Right along with our signs for Q, if enthalpy is positive, that means it's an endothermic process. If enthalpy is negative, or I should be saying change in enthalpy. If change in enthalpy is negative, then that's an exothermic process. Same as before, okay? So nothing's really changed there. As an example, okay, don't worry so much about, all the specifics of this. Let's look at the heat pack reaction, okay? You go to Walgreens, you go to CVS, you got yourself a little boo-boo or whatever, you hurt yourself, you want to get a heat pack, right? So those things that you just break, and it produces heat. Maybe it's not an injury, maybe you're going skiing, right? And those little tiny heat packs that you keep in your gloves, right? So you crack them, there's a chemical reaction that takes place inside, but we don't really care about the chemical reaction itself, we care about the energy. Well, heat pack, it feels warm to you, so what kind of reaction is that if it feels warm to you, okay? It's an exothermic reaction. As a result of the reactants going through their reaction and producing a product, the reaction itself has lost energy. The change in enthalpy is negative because energy has been lost. Whereas a cold pack, think about a cold pack, you break it, you feel it, all of a sudden now it feels cold, right? Why does it feel cold? Because the reactants are absorbing energy from your hand. That's why it feels cold. And so as a result of absorbing energy, now you've got your products. Okay, that is absorbing heat from the surroundings. Delta H is positive. So it's the same as before. This is nothing new. This is just showing you more examples of this, and once again reiterating that if delta H, just like Q, is positive, that's going to be endothermic. And if it's negative, that is exothermic. So it's the same thing as before, just more examples. Okay, so let's start to look at a thermochemical equation. I briefly introduced this in topic 9. We revisit it now. A chemical equation you're used to. A chemical equation is the reactants and the products all balanced. What makes it thermochemical is the addition of the delta H at the very end. Notice this one, delta H is negative. So what kind of reaction is this? If it's negative, this is an exothermic reaction, meaning the reactants are higher in energy than the products, because as a result of that reaction, it released energy. Here's something else. The negative, or doesn't matter negative or positive, the value that's reported over here always coincides with the balanced chemical equation. So for example, you notice that we have it already balanced, okay, a 2, 2, 2, and then a 1, right? That's our mole ratio. This energy corresponds to that mole ratio. So if I react 2 moles of carbon monoxide, 747 kilojoules of energy is released, right? If I react 2 moles of nitrogen monoxide, 747 kilojoules of energy is released. If I produce 2 moles of carbon dioxide, 747 kilojoules of energy is released. And you may have guessed it, if I produce 1 mole of nitrogen gas, 747 kilojoules of energy is released. That energy always corresponds to the mole ratio, okay? Well, what if I wanted to know, hey, how much energy is released when I react 4 moles of carbon monoxide? Well, if 2 moles releases 747, then 4 moles must be double that, right? And so that makes intuitive sense. But what I want you to understand is that this energy always corresponds to the mole ratio from the balanced equation. That's important, and we're going to see some examples in just a moment. You'll notice that, and let me get rid of some of the drawing that I've got going on here. You'll notice that the energy is in kilojoules. So the standard unit for energy is a joule, but you're going to see that the joule is such a small energy unit that when we're dealing with chemical reactions, we always have the energy in kilojoules because we're dealing with a lot of energy, all right? So let's look at some examples here. Examples 4 and 5, we're looking at the exact same thermochemical equation that I had on the previous slide. How much energy is released from 18.40 grams of carbon monoxide being reacted? Okay, so let's break some things down. So I've got grams, right? It's giving me grams of carbon monoxide, and ultimately it's asking for how much energy is released. So I need to somehow get from grams to kilojoules. That's the unit we measure energy in. Well, by now, hopefully you understand you can't go from grams to kilojoules. You can't do that. You need to go through a mediator, which in chemistry is the mole. Now, grams to mole, you should be familiar with. That's going to be our molar mass. But how do you go from moles to kilojoules? How are you going to make that transition? Well, it comes from the balanced chemical equation and the energy at the very end. So I know that for every, what are we looking at? We're looking at carbon monoxide, right? So that's right here. So I know that for every 2 moles of carbon monoxide that I react, 747 kilojoules of energy will be released. That's the relationship. So that's how we're going to solve this problem. So down here, let's set it up. 18.40 grams of carbon monoxide. First thing I need to do is I need to convert that from grams of carbon monoxide to moles. So let's figure out what that is. Let's see. Carbon's 12.01, oxygen 16. Molar mass of carbon monoxide is approximately 28.01. So my grams will cancel. Now here's what's important. This is important right here. For every 2 moles of carbon monoxide that are reacted, 747 kilojoules of energy are released. The reason there's a 2 here is because that's the coefficient right there. Whatever coefficient was there, that's what needs to go there. So the moles cancel, and now I'm going to calculate what that would be. Let's see, 18.40 times negative 747 divided by 28.01, and then also divided by 2. Looking at 3 sig figs, actually, because this is a measured value. So we're going to do 3 sig figs. 3 sig figs is negative 245 kilojoules, or you can just say 245 kilojoules. That's fine with me. The reason why is because how much energy is released? I already know it's released, so I don't have to put the negative there. I can just report out that 245 is the answer. Okay, let's look at one more. If 924.3 kilojoules of energy was released, how many grams of carbon dioxide was produced? So, very similar. We're just going the opposite direction now. So I'm going to start with energy now, and I'm going to somehow get to grams. Okay, so first thing I notice, 924.3 kilojoules of energy are released. So when I write that mathematically, I need to write it as negative. 924.3 kilojoules of energy was released. Now I know negative 747 kilojoules of energy are released for every, what am I asked to solve for? In this one, I'm asked to solve for carbon dioxide. So that's right here. So 747 is released for every 2 moles of carbon dioxide. Once again, why am I writing 2? Because that just happens to be the coefficient that's right there when it's balanced. So the kilojoules will cancel. All right, and the last thing, I don't want to know moles of carbon dioxide. I want to know how many grams. So I got to figure out what the molar mass is for carbon dioxide, which is approximately 44.01 grams. So moles will cancel, and now I can go through and calculate. 923 divided by negative 747, 2. All right, with 3 sig figs, it looks like 109 grams of carbon dioxide would have been produced if that was the amount of energy that was released. All right, we've got one more example. We've got example 6 here, but we're running out of time, so I'm going to do this one in the next video before I start section 4.